Welcome, Calculus 2 students. Today we are discussing a particular kind of first-order linear differential equation, and it is one that has the form some constant times y plus another constant. And if you do separation of variables and you solve this differential equation, you will get that your original function y of t is equal to this here, where b and k and c are constants. Okay, so we've got a differential equation that is of that form where k equals negative 0.03 and my b happens to be equal to 6. This means that I know that my y of t is going to be equal to some constant e to the negative 0.03 t minus 6 over, and that would be negative 0.03. So in just doing that little computation there, I get y of t equals c e to the minus 0.03 t plus 200. Okay, which looks like this thing right there. I need to go ahead and use my initial condition here and state that when it is time 0, what is that amount of drug that is in the blood? So at time 0, when you first get your initial IV dosage of this drug, so that would be 9.03 times 0 plus 200, and that's times 0 like this. So this equals 0, c, and that's a 1 plus 200. That gives us that our c value is negative 200. So my original y of t then is, just plugging that in, here it is right here, that would be negative 200 e to the minus 0.03 t plus 200. Now if you want to simplify this and take your 200 out, might make it a little prettier, which is what they did above right here. And we'd say that's 1, and then this guy's negative. Alright, so what in the world does this mean? So even as I continue to administer this drug into the IV line of the patient, the half-life of this drug is breaking down, and that's what that steady state of 200 milligrams means. This thing is breaking down as we're adding this drug into the blood of the patient. For our next problem, we are looking at direction fields. So I got our old procedure up here. We need to know first off when we have our equilibrium solutions. Our equilibrium solutions occur when y prime equals 0. So let's just, we'll do it over here for this one. 0 equals minus k y plus b. So our equilibrium solutions occur when y equals, move that over, b over k, when y equals b over k. So when y is some b over k value, that would be our equilibrium solution. So we'll just put it at some constant value there. And now let us consider when minus ky plus b is greater than 0. Moving that over and manipulating, we'll find that is when y is, looks like it'll be less than b over k. When y is less than b over k because of that flipping of the inequality, that would be when we have an increasing solution. So you'll notice here is my b over k solution. When y is less than that b over k, we have increasing. And likewise, I'll do the opposite. So that was minus ky plus b is less than 0. That happens when y is then greater than b over k. So I have the decreasing solution then. And this would be our stable equilibrium because we're not shooting off to infinity or negative infinity. And notice that the opposite is going to happen over in this one because we'll have our equilibrium solution, same thing, at some sort of b over k. But when ky plus b is, let's say, greater than 0, this would happen when y is greater than b over k, or minus b over k. This is going to be a minus b over k solution. So when y is greater than that, so that's why these all shoot up, and the other way, ky plus b is less than 0. These decreasing ones are going to be when y is less than minus b over k, and when y's are less than the b over k, we have these decreasing, and you see that this is an unstable equilibrium because this is shooting off to infinity or negative infinity. And this is what we're going to call direction field analysis, just being able to tell whether or not this is going to stabilize out or whether it's going to, as t gets larger as time goes on, shoot up to infinity or negative infinity. In our next problem, we are looking at a differential equation that we're supposed to, I believe this was supposed to say find and graph the function. Alright, so let's find the function first. I will note to you that k in this case is 0.005, and my b in this case is going to be negative 600, and I'll put that together for you. Okay, just putting together our solutions to that differential equation, and now putting in our initial condition where b of 0 equals 60,000, we're going to get what our c value is. Alright, we have found our function, and we have now found, this is the graph of that. After how many months does the loan balance reach 0? That loan balance, that is our b, and that would be after, and then doing the algebra for the b part, we have the 139 months is what I get, and it looks about right on that graph. So that's nice. On to the next one. Our next problem involves Newton's law of cooling, and we need to know the temperature at any time. That's what we're looking for. We don't really know our constant C yet, but I do know A. Our ambient temperature is 20 degrees, so that would be our A. Now, I know that at time 0, the temperature of our bowl is 200, so we can get our C value. So let's do that. Okay, so I have my C value now, and now my equation looks like this. I still need to know K. I have one more point. They told me that T of 2 is 160. I can find the K by using just some regular old algebra, and I'll get that K value. So using my algebra, I get K is 0.126. Drag that out quite a bit, sometimes even more so than the 3 decimal places. Just be sure you look at what they're telling you. So here's this bowl. You take it out, it's 200 degrees, and then it cools off to ambient temperature. And that's all for Newton's law of cooling, and there wasn't any calculus to it that we were supposed to do. There was calculus to getting to the solution, but not to what we did. Alright, and if you have any questions, send me an email and see me at the Collaborate.